Let us now proceed to permutation group. So, we need to show that this group is a permutation group. So, I labeled the corners of my model as 1, 2, 3, 4, 5, 6, 7, and 8. So, for our moves, let beta be the permutations for counterclockwise rotations, and let mu be the permutations for flip and clockwise rotations. So, here are the set of moves for beta and for mu. For our do nothing, which corresponds to beta sub 0, it is equal to 1:1, 2:2, 3:3, 4:4, 5:5, 6:6, 7:7, and 8:8. So for our rotate 45 degrees counterclockwise, we have beta sub 1 is equal to 1:2, 2:3, 3:4, 4:5, 5:6, 6:7, 7:8, and 8:1. Next is for our rotate 90 degrees counterclockwise, we have beta sub 2 is equal to 1:3, 2:4, 3:5, 4:6, 5:7, 6:8, 7:1, and 8:2. Next is we have the rotate 135 degrees counterclockwise. So this is our beta sub 3 is equal to 1:4, 2:5, 3:6, 4:7, 5:8, 6:1, 7:2, and 8:3. And next we have rotate 180 degrees counterclockwise, which is beta sub 4 is equal to 1:5, 2:6, 3:7, 4:8, 5:1, 6:2, 7:3, and 8:4. And next we have rotate 225 degrees counterclockwise, which is our beta sub 5 is equal to 1:6, 2:7, 3:8, 4:1, 5:2, 6:3, 7:4, and 8:5. Next is we have rotate 270 degrees counterclockwise, which is our beta sub 6 is equal to 1:7, 2:8, 3:1, 4:2, 5:3, 6:4, 7:5, and 8:6. And next is we have rotate 315 degrees counterclockwise, which is beta sub 7 is equal to 1:8, 2:1, 3:2, 4:3, 5:4, 6:5, 7:6, and 8:7. And next we have the flip only. So this is our mu sub 1 is equal to 1:1, 2:8, 3:7, 4:6, 5:5, 6:4, 7:3, and 8:2. Next is we have flip and rotate 45 degrees clockwise, which is mu sub 2 is equal to 1:2, 2:1, 3:8, 4:7, 5:6, 6:5, 7:4, and 8:3. Next is we have flip and rotate 90 degrees clockwise, which is mu sub 3 is equal to 1:3, 2:2, 3:1, 4:8, 5:7, 6:6, 7:5, and 8:4. Next is we have flip and rotate 135 degrees clockwise, which is mu sub 4 is equal to 1:4, 2:3, 3:2, 4:1, 5:8, 6 is to 7, 7 is to 6, and 8 is to 5. Next is we have flip and rotate 180 degrees clockwise, which is mu sub 5 is equal to 1 is to 5, 2 is to 4, 3 is to 3, 4 is to 2, 5 is to 1, 6 is to 8, 7 is to 7, and 8 is to 6. And next we have flip and rotate 225 degrees clockwise, which corresponds to mu sub 6 is equal to 1 is to 6, 2 is to 5, 3 is to 4, 4 is to 3, 5 is to 2, 6 is to 1, 7 is to 8, and 8 is to 7. Next is we have flip and rotate 270 degrees clockwise, which is our mu sub 7 is equal to 1 is to 7, 2 is to 6, 3 is to 5, 4 is to 4, 5 is to 3, 6 is to 2, 7 is to 1, and 8 is to 8. And lastly, we have flip and rotate 315 degrees clockwise, which corresponds to mu sub 8 is equal to 1 is to 8, 2 is to 7, 3 is to 6, 4 is to 5, 5 is to 4, 6 is to 3, 7 is to 2, and 8 is to 1. So, let binary operation star be an operation under multiplication. So, here are the results if we operate beta sub 1 multiplied to a permutation element. So, here in our first line, we have beta sub 1 times beta sub 1. So, this is equal to beta sub 2. And next is we have beta sub 1 times beta sub 2, which is equal to beta sub 3. Next is we have beta sub 1 is equal to beta sub 3, which is equal to beta sub 4. Next is we have beta sub 1 multiplied by beta sub 4, which is equal to beta sub 5. Next is we have beta sub 1 multiplied by beta sub 5, which is equal to beta sub 6. Next is beta sub 1 multiplied by beta sub 6 is equal to beta sub 7. And then we have beta sub 1 multiplied by beta sub 7 is equal to beta sub 0. And then we also have beta sub 1 multiplied by mu sub 1 is equal to mu sub 2. Beta sub 1 multiplied by mu sub 2 is equal to mu sub 3. Beta sub 1 multiplied by mu sub 3 is equal to mu sub 4. Beta sub 1 multiplied by mu sub 4 is equal to mu sub 5. Beta sub 1 multiplied by mu sub 5 is equal to mu sub 6. Beta sub 1 multiplied by mu sub 6 is equal to mu sub 7. Beta sub 1 multiplied by mu sub 7 is equal to mu sub 8. And then, lastly, we have beta sub 1 multiplied by mu sub 8 is equal to mu sub 1. So, this is the permutation table of results if we continue multiplying an element to an element. So, to conclude that this is permutation table also forms a group under permutation multiplication with the 16 moves from the geometric model that I have constructed. The following conditions must be satisfied. So, first, is this permutation group closed? Since the resulting elements were just found in the set beta sub 0, beta sub 1, beta sub 2, beta sub 3, beta sub 4, beta sub 5, beta sub 6, beta sub 7, mu sub 1, mu sub 2, mu sub 3, mu sub 4, mu sub 5, mu sub 6, mu sub 7, and mu sub 8. Therefore, the permutation table is closed. Next is this associative? So first, we need to rotate the table by 180 degrees and find a row or column that you can interchange. So as you can see here, we can interchange the rows 2 and 8, rows 3 and 7, rows 4 and 6, rows 9 and 15, rows 10 and 14, and rows 11 and 13. So if we interchange these rows, the rotated table will be similar to the original permutation table. Therefore, the permutation table is associative. So does it have an identity element? So after examining the operation table, we can conclude that beta sub 0 is the identity element because the row and column labeled beta sub 0 both reproduce all elements in the same order as the set. So this means for every element x in the set, beta sub 0 star x is equal to x and x star beta 0 is equal to x, which satisfy the condition or the definition of an identity element. Lastly, does it have an inverse element? So by examining again the table, we can say that each element has an inverse because for every element x, there exists another element y such that x star y is equal to beta sub 0 and y star x is equal to beta sub 0 where beta sub 0 is the identity element. So this confirms that all elements have inverses in the set. So based on the permutation table, we can conclude that the table forms a group under the multiplication operation. This is because the permutation table is closed as all results stays within the set. Also, the permutation table is associative and there exists an identity element that satisfies the identity property for all elements. And lastly, every element has an inverse such that their product will with the element yields the identity. Therefore, all group actions are satisfied, confirming that the permutation table is indeed a group. Let us now determine the subgroups of the permutation table. First is we have the improper subgroup, which consists the elements beta sub 0, beta sub 1, beta sub 2, beta sub 3, beta sub 4, beta sub 5, beta sub 6, beta sub 7, mu sub 1, mu sub 2, mu sub 3, mu sub 4, mu sub 5, mu sub 6, mu sub 7, and mu sub 8. So next is we have the proper subgroups. We have m sub 1, which consists the elements beta sub 0, beta sub 1, beta sub 2, beta sub 3, beta sub 4, beta sub 5, beta sub 6, and beta sub 7. Next is we have m sub 2, which consists the elements beta sub 0, beta sub 2, beta sub 4, and beta sub 6. And next we have the m sub 3, which consists the elements beta sub 0 and beta sub 4. And then we have m sub 4, which consists beta sub 0 and mu sub 1. Next is we have m sub 5, which consists the elements beta sub 0 and mu sub 2. And then we have m sub 6, which consists the elements beta sub 0 and mu sub 3. Next is we have m sub 7, which consists the elements beta sub 0 and mu sub 4. Next is we have m sub 8, which consists the elements beta sub 0 and mu sub 5. Next is we have m sub 9, which consists the elements beta sub 0 and mu sub 6. And then we have M sub 10, which consists the elements beta sub 0 and mu sub 7. And lastly, we have M sub 11 and then we have M sub 11, which consists the elements beta sub 0 and mu sub 8. And lastly, we have the trivial subgroup, which consists of the identity element beta sub 0. So here is the lattice diagram that I constructed for this permutation group, where the improper subgroup is interconnected to the proper subgroups and to the trivial subgroups.